In this video, you are going to learn about binomial logistic regression. Whenever we make these videos, we use resources from online. This is a list of different websites that we used to find the code and to help us make the code that you see here. So please visit these sites. First, let's learn a little bit about binomial logistic regression. A binomial logistic regression enables you to predict the probability that an observation falls into one of two categories of a dichotomous dependent variable based on one or more independent variables that can either be categorical or continuous. In many ways, binomial logistic regression is similar to linear regression, with the exception of the measurement type of the dependent variable. In other words, linear regression uses a continuous dependent variable rather than a dichotomous one. However, unlike linear regression, you are not attempting to determine the predicted value of the dependent variable, but rather the probability of being in a particular category of the dependent variable given the independent variables. An observation is assigned to whichever category is predicted as most likely. As with other types of regression, binomial logistic regression can also use interactions between independent variables to predict the dependent variable. About our data, remember that these data today are for educational purposes only and should not inform your opinion about the subject matter. We would like to use today's binomial logistic regression to predict whether ESL students will pass or fail an exam based on the amount of time they spent studying, whether or not they lived in an English-speaking country at any point in their life, their speaking scores on a previous test, and their age. Remember, this scenario and data are made up for the purpose of this video. First, we're going to install some packages. Remember, if you don't already have these installed, to use the install.packages function. And now we're going to load our data. And we can take a look at our data. Here we have 1, 2, 3, 4 independent variables and one dependent variable. Remember that our dependent variable is dichotomous, so 0 means fail and 1 means pass. And we're trying to put our participants into categories of either pass or fail based on these 4 predictor variables. We have age, study time for the test, whether or not the participant ever lived in an English-speaking country, and their speaking score on a previous test that they took in the class. Read through these assumptions. This is what will guide the code that you'll see that follows. This is what the regression model looks like. So first we have our dependent variable, and then we have our various independent variables, and our family of regression here is binomial. This time, instead of just a linear model, we're using a general linear model. So we'll run that code and we can see our various coefficients and some other information about the overall functioning of the model. Next, we'll run some code and this will give us our probabilities. So remember that the model is making the categorizations as pass or fail based on probabilities. So for example, a probability of less than or greater than 50% will place the various participants either into pass or fail categories. So that's what this function does. This function takes these probabilities. If the probability is greater than 50%, the participant's classified as a pass, and if it's less than that, it's classified as a fail. So after we run that, we can see that the predictions that we get are a series of either pass or fail predictions. Next up, we make a table which is called a confusion matrix. And here, this table takes this output, and beforehand in our original data, I'll show our original data again. We recorded in the real world, this is a made-up example, but imagine that it's in the real world. We recorded whether or not the student passed or failed. So this is real. We know whether they passed or failed already. We also know these other variables. We'd like to use this to make predictions in the future. In order to do that, we'd like to see how well these variables can be used to classify. So in order to kind of visualize that, we can use a confusion matrix. So the 0 or 1 represents whether or not the student passed or failed in the real world, and fail or pass represents our model's prediction of whether that student would pass or fail based upon the independent variables that we're entering into the model. So here we can see that we had a total of 55 plus 10, which is 65 students that failed. Total of 65 students that failed. And here we would have a total of 19 plus 16 students that passed. Our model is correctly classifying 55 out of 65 students that failed as having failed. It's incorrectly classifying 10 students who failed as having passed. So that's going to lower our categorization accuracy. And for those students who passed, our model performs less well, more poorly. So it's correctly classifying 16 students and incorrectly classifying 19 students who in reality passed. The following code takes that information and creates an overall percentage of accuracy for the model. So here, the overall percentage is 71%. The proportion correctly classified for passing was about 46%, and the proportion correctly classified for failing was about 85%. And we take the weighted average of those, weighted according to how many participants were in each group, and that gives us our overall accuracy of 71%. Whenever we report this later, we'd like to have some additional statistics. This is the code to get the walled statistics. This is the code to get the odds ratio, confidence intervals, R-square, or pseudo R-square, and the Holmshire-Leemshow goodness of fit test.